Okay, so let me recall where we are. So we had our definition of PAC learnability, and we wanted to extend it to more. I'm waiting for you, guys. Thank you. We had our definition of PAC learnability, and we wanted to extend it to more realistic situations without the realizability assumption. So we consider the situation where you have a notion of so data generation mechanism is through a probability distribution D over, say, x cross 0, 1. So we are randomly generated points and their labels. There is a probability of seeing a papaya with certain characteristics and with certain taste, but we don't assume that the taste is fully determined by the softness and color, and we don't assume that it's fully determined. We don't assume that it's determined by a rectangle. It's a completely general setup, right? So in this general setup, what does the learner see? Again, the learner sees the input to the learner is a sample S that consists of a sequence xi, x1, y1 up to xm, ym. And the only assumption that we make is that we assume that this is generated IID according to this distribution D. So we relax our definition very much. We no longer assume that there is a rule, that there is a labeling function. The only thing we assume is that the data that we see is a random sample from this unknown distribution. So we can think of it with this is the world. It generates phenomena, and this is our learner. The learner only sees the sample, and the learner tries to infer from the sample something about the world. So what is he trying to infer? So the goal of the learner is to come up with some good prediction rule. So what is a prediction rule? A prediction rule is a function that takes points in X and predicts their labels. What is not clear? I mean, what is there anything not clear on the board? What? It's okay? Okay. So the learner wants to come up with some good prediction rule. And now, what do we mean by good prediction rule? We want a prediction rule that has as small as possible probability of mispredicting y. So we have to, I did not give a precise definition of this last time. I kept it in an intuitive level, but let's give a prediction, a precise definition. So we define LD of H to be the probability when I pick x, y according to my distribution D that H of X will not equal Y. So note that this is slightly different than what we had in the realizable case. In the realizable case, we assumed that there was some correct labeling rule f. And what we were trying to do is to always that h of x will equal f of x. But here we don't have a fixed prediction rule f. We just generate random points with the labels. So my hope is that when I generate a random papaya, and it's either tasty or not, that my prediction rule applied to the features of the papaya that I can see will get me the correct label. But there is no fixed function. Yes?
Also, y here is y determined by f.
And there's no f. That's exactly the point. Y is determined by the random process. So the random process generates papayas and also determines randomly whether they're going to be tasty or not. Now you want a predictor that sees the papaya and can predict this random label. And of course, we don't have here a hope of being able to predict precisely. That's too much to hope for. So we will talk about in a second. So we said under such condition, the best possible H is what we call the base rule. And the base rule was that this H prime, that for every x, it looks just as the question of what has higher probability given that x. Is given that x, so we look at the probability, d of seeing the pair x with the label 1, given that we saw x. So I can ask, what is the probability that I'll see a label 1, given that the point that I saw was x? If this is greater or equal than a half, I will predict 1. If this is less than a half, I will predict 0. That's the best possible prediction rule. If the labels are random, then my best option is just to guess whether they're going to be more likely to be 1s or more likely to be 0s, and go with that more likely option. Yes?
But you can't really compute this without knowing d, right?
Right. So this is the best possible H, but of course the learner doesn't know it. This is beyond, this is not accessible to our learner. Why? Because it involves knowing the distribution D. And our learner doesn't know what the distribution D. All the learner knows is just the sample, which is a really realistic situation. Because if I don't know what is the probability of a papaya being tasty or not, all I know is that the sample that I saw, and I'm trying to learn something about the world from this sample. So this is not accessible to the learner, since the learner does not have access to the way the data is generated. The only thing the learner sees is the sample. But note that even that predictor, even that optimal predictor, of course, may make lots of errors. If I ask what is LD of H prime, so if we go back to this issue of arrow, what is LD of H star? LD of H star, in some cases, may be pretty high. Can you give me an example of a case in which LD of H star may be high? Yes?
It can be 50% if it's a coin flip.
If it's a coin flip, if the data generating process is completely random, it's a coin flip, then this rate will be a half. So this may be very high, but that's the best that we can hope to achieve. So our definition of success will have to take into account what is realistic to expect or not. Okay? It depends on the process. And it doesn't necessarily have to be even something which is completely random. It could be that our lack of ability to predict the labels just comes from the fact that what we are measuring is irrelevant. So here we were saying in the examples of the papaya that I'm measuring the softness and the color of the papaya and trying to predict why is the taste of the papaya, whether it's tasty or not, right? But maybe what I'm trying to predict is whether this papaya will have more or less than 50 seeds inside. I mean, the fruit has seeds, right? And I'm trying to predict how many seeds are going to be inside. And what I'm measuring, the color and the softness, is completely irrelevant to what I'm trying to predict. So the randomness could come from many sources. Maybe I'm not measuring the best thing, but we try to analyze the situation. What is the best that we can do? And this is our input. OK, so we will have to settle for some weaker notion of success. I will not be able, under such circumstances, to guarantee that my error is less than arbitrary epsilon. And the weaker notion of success that we introduced had to do with our class H. So weaker notion of learners' success is defined relative to some, we can call it benchmark class of functions H. So what we will say that H, so I'm trying to be as good as anybody in H. So we will say that our goal, so we'll say that H is epsilon accurate with respect to D and H if LD of my H is at most the minimum over all H's in H of LD. Oh, sorry, let's call it minimum over all H prime in H of LD of H prime plus epsilon. So my notion of success now is relative to some benchmark class capital H. I want to not be much worse than the best one in H. Before, we just didn't have this. We wanted our error to be at most epsilon. But now we are saying in realistic situations, I cannot guarantee that. And I don't even require that I will get epsilon close to the base optimal, because maybe I have no clue about what is this base optimal. So I'm getting much more modest. And I'm saying I just want to compete with all H primes that sit in some benchmark class capital H. So these are the examples that I gave you last time. Say that I'm trying to give you a guarantee that it will be good for you to invest your money with me. So I'll tell you, I will make you as much profit as any agent in this big company. So I do not guarantee success, but I guarantee that you will do with me at least as good as any agent in this big company, and maybe I'll charge you less, so you should rather come to me. Yes?
Is epsilon a fixed value, or does it have to be
No, so this is epsilon success, epsilon accurate. And then when we define learnability, we will have this, our notion of m epsilon delta, which will tell you how many samples, how much training do you need in order to guarantee epsilon success. So the smaller epsilon, the more training data you will need. Because all we see is this training data, the sample S. So the more demanding the requirement, the bigger we will need to have S. OK, so this is the game that we are playing now. We changed a little bit the rules of the game. We do not assume anything about the universe. And in return, since the universe is so unpredictable, our guarantee is going to be weaker. It's only going to be a relative guarantee. And that's what we call the agnostic learning setting. The agnostic comes to say we don't assume anything, any prior belief about the universe. And the role of H now is only as a benchmark class that we compare ourselves to. Before, H was a class from which we had the guarantee that a good predictor comes from H. Now we don't have any guarantee. OK, so under these conditions, we had this notion of agnostic, the definition of agnostic Park learning, which is very similar to the old definition of Park learning, the previous definition. The only difference is our notion of success. So let me repeat the definition. So here is the definition of agnostic, the notion of agnostic Park learning. We say that H is agnostic Park learnable if, and now I'm almost repeating word by word the definition of Park learnability. So we say there exists a function m that goes from 0, 1 times 0, 1 to predictors. So predictors, you didn't like my notation of the set of all f such that f goes from x to 0, 1, right? So another way of writing it, but I think it will be just as bad as. So let me write it in words. So here it's the set of all functions from x to 0, 1. The set, so, oh, sorry. Where is all those people that will get a point here? I'm jumping ahead of myself. So who wants the point? Yes. It goes to the natural numbers at this point. We will have this later, right? I was worried about it so much that I thought about it before it's time. Just to the natural numbers, right? OK, so email to me. And on those emails, I mean, you did it right. On the subject line of the email, write CS 485 bonus. So they'll be able to search for it later. OK, so this function. Now what do we want from this function? Yeah. What do we want from this function? So we want that such that, and now we start all our every. For every, there exists a learner, A, and the learner is this thing. A goes from samples to functions from x to 0, 1. This is my learner. There exists a learner such that for any d over x cross 0, 1 and any epsilon delta greater than 0 and any m above m of epsilon delta, we have that the probability when I pick S according to d to the m. So I'm picking a sample according to this unknown distribution, repeated m times because my sample size is m. The probability of this sample that the arrow of A of S will be bigger than, and now it's not bigger than epsilon, now it's bigger than the minimum over all H in H of LD of H plus epsilon. This probability is less than delta. So we have this sample size guarantee. You give me your accuracy and confidence parameters epsilon delta. I come up with this number m of epsilon delta. If the sample size is bigger, then the probability that my algorithm, when it sees this sample, will have an arrow which is greater than the best in capital H plus epsilon, this probability is low. So these two parameters, epsilon and delta, determine how big should my sample be. Yes?
The brackets for the minimum function end around LD of H, or is there supposed to be another term in there?
2 brackets.
Minimum over all H in H. I missed a bracket here, yeah. Minimum over all H in H of this plus epsilon. But missing a bracket is not. But good try. Keep trying. Missing a bracket is almost like a spelling mistake, and I'll make many spelling mistakes. OK, so this is our definition. And the main thing that is different than before is that before, in the realizable case, we assumed we replaced this with 0. Now we already can see that there should be difference between different classes. If I have a big class or a small class, if I have, say I have some H1, which is a subset of H2, which of them will be easier to learn? Which of them I have a better chance of learning, H1 or H2? Which is easier? H1. Why is H1 easier? Because my class is those that I'm competing with. So if I have to compete with the minimum over H2, there may be someone here who is doing better than all the guys in H1. Right? The minimum of a bigger class is more demanding. Competing with a bigger class of competitors is more demanding than competing over a small class of competitors. And note that, I mean, it's kind of implicit in the definition, but we assume that the learner knows H. What the learner knows in advance is he knows the H that he wants to compete with. That's only fair. So if H, for example, consists of only one function, is it going to be always, can you tell me how can I compete with a class if it consists of only one function? Yes? Just return that function. If I have to compete with only one function, then no matter what the data is, I'll return this function and know that I'm competing well. Right? If I have to compete with two functions, one of them is the constant 0, and one of them is the constant 1, what should I be able to do? Just to predict which label is more likely, the 0 or the 1, and go with the more likely label over all examples, not over a single example. So competing with one function is always very easy. Competing with just two constant functions, so I should see enough examples that I'll get a sense of what is more likely, seeing label 0 or seeing label 1. But as the classes grow larger, competing with all elements of H could become more and more difficult. Yes? No, so the learner, that's a good point. A of S, the function A, is a function that takes samples and output any function from x to 0, 1. It doesn't necessarily have to be an H. So see, if I want to compete, say, with the class of all agents in some investment company, maybe they're using some of software that I'm not aware of. I'm not going to do the same as them. I just want to do as well as they do. Okay? Now, it's getting harder as H grows. We will see two things. The first thing we will see today is, again, as we saw with the non-agnostic pack, that every finite class H is learnable. Then we will also see that, it would have been very boring if classes are learnable if and only if they are finite. So we will see that there are also infinite classes that are learnable. And next week, you will see that there are classes which are not learnable, which is a bit harder. To say the class is not learnable, I have to show you that no matter what algorithm you try, it's going to fail. So, which reminds me, I am not here. I'm out of town next week, so there will be a PhD student of mine will replace me. So class will take place, but it will be someone else replacing me next week. OK. There's a question here. Yes?
Should that be M subscript H epsilon delta?
Right. So now I can say, well, I can add all kind of decorations to M. I'll call it M of H. I'll call it M learnability of H. We will see. But for the definition that there exists a function. So before we go on, I want to show you that, in fact, this is even more general than what we've been discussing so far. So we can extend this to an even more general setup. And the more general setup is you can just think of it as we have some H does not necessarily have to be a function to 0, 1. And my data should not necessarily be of 0, 1. So let us consider some other learning tasks. So one learning task could be multi-class prediction. So what do I mean by multi-class prediction? That the label is not necessarily either 0 or 1. An example could be, I show you text, and I want you to predict what is the topic of this text. I show you a document, and you should be able to tell me, is this document about sports, or about entertainment, or about science, or about politics? So we have here many labels, many possible labels. So my set of labels, Y, could be a set of topics. And in the multi-class setting, so we have our, so the set of labels, the set of labels y could be larger than just two elements. So it could be, say, the topic of the document: politics, sports, entertainment, finance, many things. And I'm showing you a document, and I want you to predict which topic it belongs to. Or maybe that's what Google does when you get your email. I don't know if you have it, but it does sometimes automatically tells you this is an advertisement. This is spam. This is personal. This is, what else do we have? Social or some kind. So it tries to find the correct label for your email. So we want to learn such a function. And this function has many labels. Now the question is, how will I define success here? So I can say a failure here is whenever I predict one label and it was another label. Right? Another scenario is to have real valued prediction, which is sometimes we call it regression, where I'm trying to predict the set of labels, is the real line. So for example, I'm trying to predict the temperature tomorrow. Now, in what sense is it different than many labels? So example, predict tomorrow's max temperature. In what sense is this different than just multi-label? Yes. Yeah, but that's true. But even if I'll say I know that the temperature tomorrow is just ranging between -50 and +50, and the range is only 100 numbers, still there is a difference between prediction of the temperature tomorrow to prediction the topic of a document. Yes?
I guess like real values predictions, you have the sliding amount of correctness, whereas with the label,
Very good.
binary.
Exactly. In the labeling, in the prediction of topic, if it was politics and I predicted sports or entertainment, it was a mistake, regardless of what I predicted. If I didn't predict politics, it was a mistake. When I'm trying to predict temperature, if the max temperature tomorrow is going to be -5, and I predicted -6, it's not so bad. But if it's going to be -5 and I predicted +35, then it's really a miserable mistake. So the difference will be in how do I penalize you for a mistake. Here, every non-correct prediction is the same penalty. Here you can have a small penalty if you made a small mistake. There's a notion of small mistake and big mistake. So how do we capture those things? And now we get to the question you could have worried about it before. Why do I use, for the error, why do I use L and not E? I mean, error is E, right? And L I should have kept for my learner. And I sacrificed this important L for this. And the reason is that the L stands for loss. We call it a loss. And the loss is what you suffer if you mispredict. And loss could be something very general. So let us discuss this for a second, so we call it loss. And we can discuss it in a more general setting. So there is a more, what can we do with this guy that will not bug me all the time? There's no crack there. Okay, I'll do something. Okay, at least it's shorter. So, more general setup for learning. So in the more setup, we have a universe. We have some domain set, which is my universe. And just for distinction, I'll call it Z rather than X. And I have a set of models of the universe that I'll call M. And I'll have a notion of a loss. And the loss will be the loss of some model on a given instance. So it will be a notion of the loss of a model M. So let's not use M, let's use H. So H is my model now. I cannot use M because I kept it for the sample size on some instance Z. And now it will make sense in a second. And now we have there is the universe or the world, whatever how you want to call it. The data is generated by some unknown distribution over Z, and we aim to find the best model for this unknown distribution, for that distribution. So we will define the loss with respect to a distribution D of an H on the loss with respect to a distribution D of some model H as the expectation when Z is generated by my unknown distribution D, the expectation of LHZ. So I have a notion, I have a model of the universe, and for every point, what we saw before is that if I was correct, my loss on the point was 0. If I was not correct, my loss of the point was 1. And I wanted to minimize the expected loss when the point is generated from distribution. So if I want to make a more clean translation between the new interpretation and the old one, so what we had before, so far, my Z was some X cross 0, 1, and my models M was functions from X 2, 0, 1. And L of a function h for my model and the z. Now, z for me, you see, z is a pair, x and y. So L of h on a point x, y. This is a point z in my space. What was my loss? It was 1 if h of x was wrong, and it was 0 if h of x was the correct y. So what I'm saying is that under this translation, the LD that we saw before is exactly this. So under this translation, how did we define our loss here? Do I have still the definition of loss here? No. So we defined our loss. We define our loss as the probability of making an error. But the probability of making an error is exactly the expectation of this function that is 1 whenever I make an error, or 0 when I don't make an error. Or it's the average number of errors that I will make. So now LD of H coincides with our previous definition that was LD of H was the probability when I pick x, y according to D of the error of H, of the probability that H of x is not equal y. So the probability, you see, if H of x is not equal y, I'll see a 1. If H of x is equal y, I'll see a 0. And the probability that I'll see a 1 is exactly the expected value of my loss. So what I'm saying is just that we can review what we did before and say there's a more general setting. We are looking at you have a model that tries to model the universe. We have a notion of loss. We want to minimize the expected loss. OK, so let me stop. I will now go back to the other examples and show you how we can model them by different notion of loss. Does it make sense at this point? Any questions? So if we go back to the other examples, so all I'm saying is that everything that we did before still applies with this more general notion of learning. So let me consider the examples that we saw. So this was the first example. Maybe I'll leave it. OK. So the examples that we saw, first example was a binary label prediction. That was the old stuff that we did with the papaya, tasty, not tasty. And what we defined was LH of Z. Z was X cross 0, 1. And LH of a point Z, of a point XY, was 1 if H of X equals y, not equal y, and 0 if H of X equals y. So that was the old setting. Now, what do I do if I want to consider the multi-class setting? Multi-class prediction. So now my set Z is going to be X cross some set of labels Y. This is the set of topics. So in my set of labels here, I could have politics, sports, entertainment, and so on. This is my set of topics. And can anybody tell me what will be L, the loss of some H, when I see a document and its topic? How am I going to define my loss? Yes? Square of what? But there's no y, there's no minus, because y is a set of topics. It's a set. How do I do politics minus sports? Yes.
It's 1 if you're wrong and 0 if you're right.
Right. It's 1 if I'm wrong and 0 if I'm right, just like here. Yes.
Shouldn't h of x equals 0 be h of x?
A equals y. Oh, now you got your point. Right. Equals y, right.
Is it a point?
What?
Is that worth a point or not?
It was a point. I mean, it was an easy one. Yeah. Don't worry, I will not run out of points. Okay, so LH here will be again. It will be 0, 1 if h of x is not the correct label, and 0 if h of x equals y. And these are called the 0, 1 loss for the obvious reason. The loss is always either 0 or 1. You made a mistake, you didn't make a mistake. But now let's look at the regression problem, or the weather prediction problem. In the weather prediction problem, so example 3, regression, like the weather prediction. Predicting temperature. So here, my set Z is x cross the real numbers. And I have a model. The model sees the measurements of today and trying to predict tomorrow's temperature. So now I have to define what is going to be L of my H. H is a predictor that sees tomorrow's data and predicts sees today's data and predicts tomorrow's temperature. And it gets as an input, it gets a point which is the measurements of today and tomorrow's temperature. Say T. So what is going to be the loss now? And I can use different losses. But one common loss that people use here, you want to suggest something?
Well, you could use square distances.
The square distance. So square distance is very common. So we use here L of x, h of x minus t square. This is called the square loss. And note that this is different in the sense that you have a notion of big mistake and small mistake. You suffer less if you made a small mistake. And again, I mean, everything that we will do about learning applies to those settings as well. So what we are trying to minimize is the expected square loss. We're trying to find a predictor, a rule that will minimize the expectation of our loss. Let me give you one more example before we move on, which looks completely different. So, a third example, which is quite different. What? What did I say? Oh, 2 3s. That's not a point. Okay, so my last example is sometimes it's called clustering, but I will call it representing data by k code words. So this is something which is useful say, if I want to transmit audio signals. So it's much easier for me to take the audio signal, which is analog, and turn it into digital. And even simpler, I will have a collection of audio signals, and I will try, so I will have I want to model the world. So the world of all audio, say it is some high-dimensional space, but let's draw it in 2 dimensions. So you have some distribution of audio signals that I'm going to be getting. And now I want to pick, do I have colors here? No, I don't. I want to pick k code words to model this world. If the world is really, if the audio signals are really kind of distribution that have modes on those, around those code words, they could be a good modeling of the world. I want to simplify the world. Rather than giving you an exact analog signal, which will require infinitely many digits, right? I want to represent it by only few. I only have capacity of k many code words with which I want to model the audio signal. So my universe is just going to be, Z is just going to be some high-dimensional space, RD. The audio messages say they live in some high-dimensional real space. And my set of models is the set of all vectors of k members of RD. So I pick some k code words. So a code word H looks like a C1 up to CK. These are the k code words that I pick. And what is going to be my cost? What am I going to pay? So now I have some H, which is my hypothesis is C1 up to CK. This is the set of code words that I fixed. And now I see some data point. I see some data point Z. What is going to be my cost? How well do I model this Z? You see what I say? I have those code words. I'm trying to every signal to model by one of my code words. So what will be kind of the cost of my coding? Yes?
The distance to the nearest.
The distance to the nearest, right. So this is going to be the minimum over I between 1 and k of the distance between ci minus z squared. So here I was trying to model the universe by k representatives. And now I see an element of the universe. I say I'll model it by the closest representative. And what I'm paying for is the distortion. How far is the closest among the representative that I have at my disposal to this point z that I picked? I mean, if you find it difficult to follow this example, don't worry about it too much. It's just an example. But what I want to demonstrate is this setup of learning that we are talking about is very general. It can capture lots of phenomena, not just predicting the taste of papaya. Don't get the wrong impression that machine learning is about papayas. Yes?
What about probability regressions? Like the probability that it would be one of the labels?
You ask what, I mean, the probability is captured here because the universe is random. We have this distribution D that it could have different probability on different label.
I meant a learner function that returns a probability.
Okay, so that's a good point. I was all the time, my models are always deterministic. A labeling function is always takes the data and gambles on a specific output and is not giving me a probability, right? We will see later, you will see it in your first assignment, that you cannot do better with probabilistic prediction. So deterministic prediction are as good as you get. By allowing probabilistic gambling, you're not getting better. If you have some probabilistic gambling, pick the outcome with the highest probability according to your rule. And it will do just as well. But we will see it formally. OK, so all that we wanted to say here is that this definition of agnostic pack learning is very general. It could handle many scenarios, not necessarily 0-1 prediction. And therefore, I use this notation LD of H, which is the loss with respect to the probability of my model or hypothesis. So I pick the hypothesis. I have a notion of my expected loss. And I want it to be as good as the best in the class of models, which is my benchmark class, plus epsilon. And I'm asking how many samples will I need for that. OK. So how can we learn in such a general and probably demanding situation? So the first learning paradigm, we call it learning via uniform convergence. Now, the name means nothing at this point, I know, but we will soon fill it with content. So what do I mean by, at this point, learning via uniform convergence, the only meaning of this title is that it directs you to a specific chapter in my book. But I will explain it in a second. OK. So what do I mean by learning in uniform convergence? So our problem is as follows. We are trying to find a model that has small loss over the world, that somehow reflects the world very well. But we don't know what is the distribution. All that we know is a sample. So we can ask in what respect, how well does the sample represent the distribution? Some samples are good. They represent the distribution very well. Some samples are bad. So we define a notion of, so our next definition. And let me, for concreteness, after we open the scope so much, let me just, for concreteness, zoom back again on the 0-1 prediction. So that things will be more concrete. So definition is that I say that a sample S equals X say Z1 up to Zm, but I will soon, they're just pairs of points. Or S equals X1, Y1 up to Xm, Ym is epsilon representative of a class H with respect to a distribution D if for every H in H the loss of my H with respect to the sample minus the loss of my H with respect to the distribution is at most epsilon. So I need to define what is the loss with respect to the sample. the loss with respect to the sample, we can think of it as if the loss, if a distribution is just uniform over the sample. Or in other words, where LS of H is just 1 over m, sigma I goes from 1 to m of 1 over m, say, z in S of the loss of H on Z. So I'm saying the loss of my H on a sample is the average loss on the points of this sample. How did we call it 2 lectures ago when we talked about PAC learning? That was the empirical loss. ERM is the empirical loss minimizer. So this is called the empirical loss of H. This is what we can see. So we want to find an H that have a small loss with respect to a distribution. All that we see is a sample. We say that the sample is epsilon representative if the loss that we measure on the sample is a good approximation of the true loss. So this is a good sample. If I have such a sample and I want to find a good hypothesis with respect to the true distribution, how can I use my sample to find a good hypothesis? If I know that my sample is representative, how can I find a good hypothesis with respect to a distribution? I'm sure that you know. I just want to see more responses. Yes?
Run your learning algorithm on the sample.
What do you mean run your learning algorithm? I don't know. What should I do on the sample? ERM. I'll do empirical risk minimization. Right. So empirical loss, sometimes we call it empirical risk. Statisticians are very what's the word? They care a lot about whether you use the word loss or the risk. So for the empirical, it's always risk, and the loss is the true loss with respect to distribution. I tend to confuse these two notions. So this is the empirical risk of H, and the loss is used only for the true loss. But I don't mind if you confuse it as well. So, OK. So the point is that if S, note that if S is indeed representative of D with respect to H, or representative of H with respect to D, then ERM H is a good learning strategy. If I have a sample which is representative, then if I minimize the loss of the sample, and this is something I can do because I do see the sample, it guarantees that I'm also doing pretty well with respect to distribution. So now I want to phrase it more precisely. So we can phrase it as a result. So let's call it a claim. So let's call it a claim. And it will say that if S is representative, epsilon representative of H with respect to D, then for any ERM H function H of S, we have that LD of H of S is at most the minimum over all H in H of LD of H plus 2 epsilon. So what I'm saying here is if a sample is epsilon representative, optimizing with respect to the sample gives you a pretty good guarantee that you are optimizing with respect to the distribution. If you know that your sample is epsilon representative, you can just do ERM with respect to the sample. Do the best on the sample. Any questions about the statement of this claim? Yes. Why did I come up with twice epsilon? Let's look at the proof. Yeah, that's the twice, at least, I mean, the benefit of this 2 here is that I hope that it wakes you up, that calls your attention that there's something not completely trivial here. Something is happening here. I'm not just playing with definitions. Yes?
Why there's something like L with subscript D like appears at left-hand side and right-hand side?
Okay. I'm coming out with the hypothesis HS. Now what I care about is what is its loss with respect to the true distribution. And what I want to compare it is to the loss with respect to the true distribution of the best function in my benchmark class.
So the H is different.
H is different. This is HS that my ERM picked, and this is any H in the class. That's where they're different. Yes?
Are you saying anything about the finiteness of S?
No. I don't say anything about the finiteness of S. I assume that S is finite, but I don't say anything about its size. I assume it's finite because otherwise this 1 over M is not defined. This is 1 over the size of S. Yes?
Is HS a member of H?
Not necessarily. Oh, HS is. HS is. Why is HS a member of S? Of H. Why is the member of H? Yes?
Isn't it competing with all the...
No, but because we just says ERMH. ERMH is defined as pick a member of H that minimizes the empirical error. So it is a member of H because I'm running an ERMH algorithm. You remember we said an ERMH algorithm is an algorithm that doesn't pick an arbitrary hypothesis. It picks an hypothesis from H that minimizes the loss. This is our guard against overfitting. So it is picked from H. Okay, so let us just see the proof. The proof is I want to bound this LD of HS. So I will make steps and you will, I'll try to ask you about the justification for those steps. You have another question?
Yeah, this question, how do we know that HS has to exist?
Oh, what do you mean?
Well, HS doesn't necessarily have to exist. You can have like an open set of...
Right. So, this is a sophisticated question in a sense. Let us assume that the minimum exists. Yeah. He's asking, what if I have an infinite sequence of hypotheses that each of them is slightly better than the one? But since my loss, you see, my loss here is just 1 over m, this sum, it cannot go infinitely down without hitting 0. Because this is 0, 1 here. In this case, this is just 0, 1. So this is just 1 over m. This number is just a number that takes values I over m. OK? In the more general setting, it's an interesting question. But here, it's not a problem. OK, so let us do the steps. So what I'm saying is LD of H of S is at most LS of HS plus epsilon. How do I know this? How do I justify this step? Anybody that has not spoken yet today? Yes?
By the definition of epsilon representative?
Right. This is by definition, since S is epsilon representative. And HS belongs to H. So epsilon representative means that your true arrow is not more than epsilon away from your arrow when you measure it with respect to S. Now the next step, I'm saying that this is less than the minimum over all H in H of LS of H plus epsilon. Why is that true? So now here this is what my algorithm picked, my ERM algorithm picked. And now I replace the HS by any H in H. And I'm saying this is still true. How do I justify this step? Yes? Because it's ERM algorithm. Since HS is ERM H. So it picks one with the minimum arrow. So I picked one with the minimum S arrow. So by definition, it beats anybody else in terms of the sample arrow. Yes?
How can you possibly have any case where the equality is not strict? Or where the inequality is not just equality?
Oh, because it is where it's not strict.
Like, how is it possible that
Because among those things that I take minimum, HS lives here. HS is one of the candidates that I'm competing with.
yeah, so why is it not just the equality?
Oh, because I want to show you that I'm beating everybody in H, not just myself. I pick HS, which is ERM. You see, my goal is to get here, to get to the minimum of all H's in H. So I say, since I picked the minimum loss one, the minimum risk one, it is better than any other thing I could have picked. Maybe I don't understand your question.
Be L subscript D of H?
I don't know yet, because the ERM algorithm only compares arrow with respect to S. The ERM algorithm doesn't know D. It only knows S. So it compares S arrows. You picked one with a minimum S arrow. And now I'm saying my last step is I'm saying that this is less or equal than the minimum over all H in H of L D of H plus epsilon. And that's where I got my two epsilons. One epsilon was already here, and now I added a new epsilon. Why is this the case? How do I, first of all, notice what changed between these two. I added an epsilon, that's obvious. But what else did I change between this line and this line? Yes? What? Ilan? Yeah, the S was replaced by a D. And why can I replace the S by D without paying more than epsilon penalty? Because it's epsilon representative. This is, again, since S is epsilon representative. Epsilon representative means whenever I want to exchange loss with respect to S with loss with respect to D, I'm paying at most a margin of epsilon. So I got that the loss with respect to the true distribution of the ERM outcome is at most the best in the class plus 2 epsilon. That's the claim that I had here. Yes?
I'm so confused about the last point. I think I agree with the point that was made, but maybe I misunderstand something. Why can't you replace the less than or equal to with an equal? Because I think
Here?
it's actually equal. The LS of H of S is equal to min. Because, well, it can
It equals to mean. I agree.
Okay.
It equals to mean. It equals to the mean. I mean, because I picked the minimum. I can replace it by the minimum. But yeah, I could write equal. Okay. I could write equal, but the less or equal is also correct, right? It is exactly equal because I picked the minimum, right? Yeah. Okay, so you should thank. Yeah, okay. So what is the conclusion? The conclusion, I mean, we are just making our first step. And the first step is saying, if I could find a representative sample, then it will guarantee that ERM works. That's what we showed here. If we could find representative samples, then on representative samples, ERM would do a good job. So the next step, I'll just mention the step and then this lecture ends. So the next step will be to show that if a large enough S is picked at random by D, then with high probability such S will be epsilon representative of H with respect to D. So now if you want to prove that we can learn, we will just prove that if we pick a large enough sample, this sample is likely to be representative. And if the sample is representative, we have a guarantee that ERM will give us a good result. Okay? So we replace the learning task by saying, let's find an epsilon representative sample and then do the work on the sample. The work will be in showing that when we take samples randomly, if they are big enough, they are likely to be epsilon representative. Okay, so as I told you, next week, Hassan, my PhD student, will replace me, and I will be back on Wednesday, 10 days from today. Have a nice week.